high like this. So if you have a current density going from 13 to 16 and the voltage going from this value to this value, fill factor nearly the same. Efficiency goes up from 5.1 to 6.3. So with the additive, the efficiency is improved. So that is the point here. You see here the incident photon current conversion efficiency IPCE with additive, without additive. So it enhances its activity as a solar cell. And again, with the time, what happens? The stability of carbon-based perovskite solar cell device based on this additive stored under dark ambient conditions. So with the additive, if you see the efficiency stays for a long time like this, then it deteriorates. And if you see the current density with the time, it's nearly steady. There is no big loss. And with the time, the voltage from the cell is nearly steady. But what happens is the fill factor, for whatever known reason, unknown reason, comes down. As the fill factor comes down, you find the efficiency comes down. But I understand the fill factor is more a phenomenon from the process of taking the cell. Maybe we'll have to look into more carefully so that this fall is reduced or avoided. In that case, the cell efficiency will continue to be the same for a longer time. So here, the freshly made perovskite solar cell, the same cell after 75 days, the cell efficiency comes down like this. And for the cell efficiency coming down, it is not the current density, not the voltage, but the fill factor which is responsible. And so the researchers will have to look into the reason for this if it is to be improved further. So this one slide tells you as prepared cell, the efficiency different earlier case. This is the perovskite precursor. It is yellow in color when you put the solution, and when you heat it on the hot plate, it becomes black. Like this. And additive, higher value, still bigger additive, and then this additive. So we increase the additive value stage by stage. Then we make the perovskite material, and then we study what happens. We make the cell, we study the efficiency, and we find at a particular value of additive, the cell efficiency is the maximum. PUD of additives, that is what we are seeing here. This is a very interesting slide. The thermogrammetric analysis of MAPBI3 powder and with PVD of additive. With additive, you get the TGDT curve like this, and pure material gives you, if you see them carefully, you find there is a dip here, whereas nothing happens here. So this PVDF addition just ensures that there is no moisture getting into that, and so the stability is enhanced. You do this with monolayer as well as double layer carbon-based solar cells. Monolayer mesoscopic carbon-based perovskite solar cell device, what you are seeing here. The current density versus voltage curve is like this. And here, for a concentration 5 mg per ml, you get the best result. And when it comes to this curve also, you see for 5 mg, you get the best result. So, keeping the dopant or the additive value different, when you make various runs, you find out corresponding to what additive value you get the best result. So, this is the pure material, and then this is the additive used, and the various parameters, the JSC, EOC, fill factor, efficiency is calculated, and the sheet resistance and the RF resistance value. If you see all the data, I have highlighted here corresponding to 5 mg per ml, the efficiency is 10.9. Thus, against various values, is the efficiency. This is the highest efficiency. And we also see the reason for this being the highest value. Double layer mesoscopic carbon-based perovskite solar device, the double layer device. Here, in this case, 1 mg per ml gives you the best performance. 1 mg per ml gives you the best performance. And so experimentally, what we have found out is when you put the pure material, when you put the doped material, when you make the solar cells in this double layer configuration, you get efficiency 12.4. The best we have got so far in our laboratory, and we hope to work more and get better results. But this is today's our best efficiency result. This is something interesting again, the shelf stability of double and monolayer mesoscopic one, and this is the double layer result, this is the monolayer result, and the with the time, number of days together, the pure material and the doped material, the pure material and the doped material. And here, very surprisingly, as time moves forward, we have done up to 60 days, and you find this is, yeah, you don't know why. If it is real, something very interesting. You have to wait for some more days and see what happens. But surprisingly, after some days, the efficiency is not deteriorating, it is increasing. We have to check these results. If they are real, we must be able to give an explanation why it is so. Efficient and moisture stability carbon-based perovskite solar cells via polyvinyl chloride. This material is additive. So this polymer additive into perovskite film exhibits a strong hydrogen bonding with fluoropolymer and acts as a hydrophobic transmission. And here you see the current density, voltage, and this is the pure material. This is this additive hard material. And with the time, current conversion efficiency is pretty like this. For the pure material, it deteriorates very fast. Optical microscope can be a big help for most of the studies. This material, here you find the different images. This is for the pure material, and there are several holes which are there. With the additive, these holes are disappearing, and you get a pattern like this. The 5-8% PVDF added perovskite. When you go for the XRD, you get the best peak, tallest peak, showing that it is crystallinity is the best, and fluidity of maximum value increases. The crystallinity is like this. And so, corresponding to the 5-8% PVDF HCFP, the results are the best. And similar studies with PGDTA and FTIR. Similar studies again with absorption spectrum and PL spectrum. Schematic diagram of carbon-based perovskite solar cells. The current voltage curve of carbon-based perovskite solar cells with a different weight percentage PVDF HFP. So you see here, corresponding to this particular value, the curve is the best. The current voltage parameter of carbon-based perovskite solar cell, the different weight percentage of PVD of HFP. So you have series of data taken, and I have highlighted this particular value which gives you the best result. Cell efficiency leads to 7.11%. And everywhere you find there's a big improvement in JSC, USC, and here your fill factor, there is an improvement. The quantum efficiency, the highest value for this additive, and shelf life again with the time to find without any additive, the pure material deteriorates very fast, whereas the additive just ensures the deterioration less fast. So after 30 days, the shelf life of 5-8% devices retain 86% for its initial PCE. But if you see, make a comparison with silicon solar cells, those cells are there for about 20-25 years. It takes such a long time for them to come down in their efficiency. As other solar cells, they are nowhere near silicon today when it comes to stability. But in terms of efficiency, many of them are very good. And so if the stability aspect is attended, is solved, then these cells may find it their way for commercial situations. So friends, the summary of what you have seen so far is what you are seeing here. After seeing a few general slides, I showed you The results got in our laboratory by my colleagues, and one-step solution processable with polymer additive approach to grow high-quality perovskite films was taken up by us. There's a lot more to be done, and this is such a huge area where a number of activities can be made, and it is endless. And we have been trying to do our part here. The influence of polymer additive in perovskite films was studied with XRD, photoluminescence, UV visible, FTIR, and thermogrammetric analysis. We could understand most of the results through these studies. Carbon-based perovskite solar cell shows higher efficiency and improved stability by additives engineering approach. Suppressed non-radiative recombination and lower trapped state perovskite shows maximum USC. These are the conclusion points to be given as summary. So if you want to have a perovskite solar laboratory for the kind of activity in our laboratory, we went in for these facilities: a glow box, a spin coater, temperature controlled hot plate, magnetic stirrer, high temperature muffle furnace, substrate cleaner. And it costs about 40 lakh rupees for these facilities alone. These are the facilities which we have seen already. For characterizing whatever we synthesized, whatever cell we made, we are making use of this facility: thermal operation, FTIR, UV visible. This is our glow box, the solar cell efficiency, PV, quantum efficiency, thickness profilometer, spectrophlorometer, electrochemical oxidation, TGDTA. All these facilities do exist with us, and so luckily for us, for our perovskite activity, most of the facilities are available in our laboratory, and for very few studies you may have to take outside. Thank you.
Thank you so much, sir, for your presentation. Dear participants, we are waiting for your questions. If you have any questions, kindly type in the chat box. Dear participants, we are waiting for your questions. Thank you so much, sir.
Thank
It
you.
seems that there is no questions among the participants because of your clear presentation.
They can contact me later also.
Sir, actually, we are having few questions, sir. Let me spell out that. Instead of SI, any other material give more efficiency?
I understood the question only partly. Can you repeat the question?
Dr. Prakash, please kindly repeat your question, complete your question.
What is the question?
Sir, it's audible.
Yeah, please go ahead.
Sir, instead of silicon material, can we use some other material for improve the efficiency of the solar cell?
Improving efficiency is one thing. Getting the efficiency for years and years is another thing. Today, of all the materials commercially exploited, silicon is in the very, very top. It gives an efficiency, good efficiency for 20, 30 years. There is no one material close to silicon in terms of cost, in terms of efficiency, in terms of stability, in terms of environmental safety. In all these aspects, silicon is the best. Other things, there are plenty of research activities going on, but time has not come to replace silicon. This is the correct situation globally when it comes to photovoltaic. Have you understood, sir?
Yes, sir. Thank you, sir. Thank you very much.
Any other questions, dear participants?
Any other questions from participants? Any PG students? You can ask Tamil also. Sir?
So thank you so much, sir, for your wonderful session. Let us move on to the next session. Thank you for honoring us by your presence, and PPG College of Arts and Sciences is blessed to have you, sir. Thank you so much.
Thank you for inviting me. I enjoyed talking to you all. Thank you very much.
Thank you, sir.
Take care.
Program coordinators, kindly proceed with the next session.
இது சொல்ல மைக் ஆன் பண்ணாம இருக்கு.
The next session will be by 11:50.
A few seconds, Ashwin.
Okay, okay.
Your voice is not audible, Ashwin.
Okay. Now, is it okay? Hello? Am I audible? Hello?
Ashwin, not audible, your voice.
No, just wait. Now? Am I audible now? Hello? Am I
Yeah,
audible now?
okay, okay.
Yeah, I can hear you. Can you hear me? Hello? Hello? Am I audible?
Yes, sir, you're audible, sir.
Okay, okay, yeah. So can I start now?
Yes, sir.
Just a
Yeah,
minute,
okay.
just a minute, Ashwin. Just a minute.
Ah,
Good noon to all. Welcome back all to the next session of ICES 2K81. I would like to invite Dr. V. Mohan Kumar to introduce the chairperson of this session.
Yeah, good morning to one and all. Welcome back to the session. So it's my pleasure to introduce our chairperson. So Dr. Jayalakshmi, Assistant Professor in Satyabama Institute of Science and Technology. She completed her degree, doctoral degree from Satyabama University. To her credit, she has published over 20 articles in reputed international journals. She has obtained patent in design of novel electrostatic spray machine for killing locusts and one time registered in the item solar mobile charger in 10 power. It is my pleasure to introduce Dr. Jaya to chair this session.
Yes, sir. Thank you. Am I audible, sir?
Yes, ma'am. You can.
Yeah. Yeah. Warm greetings to everyone present in this virtual conference. So, thank you for the organizing committee to invite me. So, it's my immense pleasure to introduce about Dr. Ashwin Kishore, sir. So, first, I would like to convey my best wishes to the organizing committee to achieve a grand success for this virtual conference. So I take this opportunity to introduce the speaker, Dr. M.R. Ashwin Kishore, sir, to the virtual audience. Dr. M.R. Ashwin Kishore obtained his doctoral degree in the area of computational material science from the Central University of Tamil Nadu. Upon his doctoral degree, he was awarded a postdoctoral doctoral fellowship from Uppsala University in Sweden. He is currently working as a postdoctoral research associate at University of Seoul, South Korea. To his credit, he has published over 20 articles in a peer-reviewed international journals with a high impact factor, and also he is a reviewer for prestigious journals too. He has organized several conferences and delivered more than a number of invited lectures in various universities around the world. Once again, I take this opportunity to invite Dr. Ashwin Kishore, sir, to deliver his lecture. Over to you, sir, please.
yeah. Thank you, ma'am, for the introduction. And I would like to thank the organizers, especially Dr. Morgan, for giving me this opportunity to present my results. Just wait, I will share my screen. Can you see the screen now?
Hello, sir.
Can you see the PPT?
Nothing will be visible. Your face won't be visible.
Okay. Now can you see?
Yeah, it's visible, sir. You just
Yeah,
make
Ashwin,
it
go
zoom.
to full screen mode, Ashwin. Please go to.
Yeah.
Yes, sir. Yes, sir. Now it's visible.
Okay. Yeah.
Yeah.
Okay. So good afternoon, everyone. I will talk about the first principles modeling of 2D materials for catalysis. So we do. Hello. What is happening? Hello. Hello, someone is talking, right?
Yeah, Ashwin.
Someone is talking in the background, right?
Yeah, that's why I'm participants, but we don't know who's this.
Okay, then I will carry on. Okay. So we do density fractional theory to study the catalytic properties of materials. So DF is a computational modeling tool to investigate the electronic structure of many body system. I hope Dr. Karthikeyan will give you a brief introduction to DFT later today. So this is the overview of my talk. I will start with the basic principles of photocatalytic water splitting and electrochemical CO2 reduction. I will explain about nitrogenated holy graphene, and then the strategies we used to improve the C2N for water splitting. And I will also, show some of my results on, the mechanistic insights into the reaction, the reaction mechanism involved in hydrogen evolution reaction and oxygen evolution reaction in BeN2. And later CO2 reduction reaction on rhodium intercalated SiC graphene. And then I will conclude my talk. Yeah, fundamental principles of water splitting is, when the sunlight is irradiated on the semiconductor or photocatalyst with a photon energy greater than or equal to the band gap energy, the electrons from the valence band, gets promoted to the conduction band. So these photo-generated electron and holes, they migrate to the surface where they participate in the redox reactions. So these photo-generated electron and hole pairs, they act as reducing and oxidizing agent to produce hydrogen and oxygen. So this particular reaction of splitting water into hydrogen and oxygen is an uphill reaction. So that means the band gap energy of your photocatalyst should be greater than 1.23 electron volt. Whereas in the case of carbon dioxide reduction, because of the human activities, there are a lot of CO2 in the atmosphere. So we need to reduce the CO2 in the atmosphere by capturing them and converting them into useful fuels or chemicals by using a catalyst. So I will show some of my results on water splitting and then the CO2 reduction reaction mechanism. Nitrogenated holy graphene. It's a 2D material synthesized experimentally by Mahmood et al. Using a wet chemical synthesis route. So this 2D structure is kind of similar to a graphene, but with the periodic inclusion of nitrogen atom and holes. So this nitrogen atom and the holes, they open up the band gap in this material. So it's a direct band gap material. And it has, the inclusion of nitrogen and holes. This make this material interesting for various applications like optoelectronic application, gas sensor, or catalysis. So we want to check whether this material is a photocatalyst or not. At the same time, how to improve the photocatalytic water splitting. There are a lot of strategies you can use to improve the water splitting. You have to first reduce the band gap and then push the absorption energy into the visible region. At the same time, the bandage pushes to straddle the water redox reaction. So here we use substitution. We substituted isoelectronic ions at the carbon site, and then the isoelectronic ions at the nitrogen site. And we also study the influence of the halogen molecules on CO2N for photocatalytic water splitting. And we also constructed heterostructure with CDS monolayer and CDS monolayer to improve the water splitting. So first we will see the stability. We will look at the stability of the pristine C2N monolayer. So for that we calculated the phonon spectra. It's a phonon spectra. You can from this figure we can see that all the vibrational modes are real. They are positive, and there are no frequent imaginary modes. That means the material is dynamically stable. And then to check the material is stable at room temperature, we performed the ab initio molecular dynamics at 300 Kelvin for about 10 picoseconds. So the total energy fluctuation is minimum throughout the simulation period, and the inset shows the structure at the end of the simulation. The structure shows a little buckling, but it does not suffer a drastic structural distortion. So that means this structure is stable at room temperature. Then we substituted a silicon germanium tin at carbon site, and then we calculated the density of states using HSE06 hybrid functional. So when we substitute these isoelectronic ions, the band gap gets reduced considerably. And there is a reduction. This significant reduction in band gap value because of this substitution. This leads to redshift in the optical absorption, and this observed redshift in the optical absorption favors absorbing more visible light from the solar spectrum, and that also improves the catalytic water splitting. The interesting thing is we calculated the bandage positions with respect to the water redox potential. So in order to have the water splitting reaction, your valence band maximum should be lower than the oxidizing potential, and then the conduction band minimum should be higher than the reducing potential. So if you see the pristine C2N, thermodynamically it is favorable for water splitting. However, the valence band maxima is located far away from the oxidizing potential. So this creates the low driving force for the holes to transfer. So this will make an imbalance between the redox reaction, the reducing and oxidizing reaction. But in the case of substituted system, say silicon and germanium substituted system, the band gap gets reduced. At the same time, the bandage positions located closer to the reducing and oxidizing potential. That means there will be a smooth transfer of charge carriers to the water redox species, and that will convert that will split the water into hydrogen and oxygen. So in compared to the pristine, the substituted system are promising for water splitting reaction. Whereas in this case, the SN is not favorable or otherwise unsuitable for the use of water splitting because the valence band maxima is really higher than the oxidizing potential. Similarly, we have also done the isoelectronic substitution at the nitrogen site. We doped phosphorus and arsenic at nitrogen site with different composition. This is the band structure of the C2N and then the substituted system. And we also calculated the band gap and then cohesive energy. If you see the band gap value, the optimum band gap for water splitting is around 1.8 to 2.2 electron volt. Interestingly, the substituted system, fall exactly in this optimum band gap region. So these are the promising material for water splitting in terms of the band gap, and they are also direct band gap material. And we calculated the effective mass of the charge carriers, and the effective mass is inversely proportional to the carrier mobility. So if you have a lower effective mass, then the carrier mobility will be high in your material. So your material should have good carrier mobility in order to have a really good efficiency. So we calculated the effective mass of electron and then effective mass of hole along two different the directions, like along gamma to k here and then gamma to m. So at least in one crystallographic direction, the effective mass of charge carrier should be lower than 0.5 m naught in order to have an excellent mobility. If you see here along gamma to k, so the substituted system, it is around 0.23, 0.26, and here 0.27, 0.24. So these are the promising material for water splitting because they have a optimum band gap value, and then the absorption spectra is also in the visible part, and then you have a really good carrier mobility. So these are the promising material. 1, 2. So these two are the promising material for water splitting. And now we want to check the bandage positions. So we have aligned the bandage position with respect to the water flux potential with two different pH, at pH 0 and then pH 0 from pH 7. You see here this the phosphorus substituted and then there's an substituted. They are promising for water splitting because they have a really well aligned bandage position with respect to water flux potential. Then we also calculated the absorption spectra, and you can see compared to the pristine one, the substituted system, they have the absorption edge more into the visible part. So that means they can absorb the abundant visible light from the sunlight and then split the water. So this will also increase the efficiency of this efficiency of the water splitting. Yeah, and then the next study we want to check whether the hydrogen halogen adsorption on C2N affects the water splitting. So we have make a supercell of the C2N, and then we put the hydrogen halogen molecule on top of the material in different positions, like on top of carbon, on top of nitrogen, the bridge sites, then the holy sites. And then we found that the molecule prefer to stay on the holy site. Then we calculated the electron localization function because it gives you can predict the nature of a chemical bond or the electron density distribution in the atoms. You see here, usually if the electron localization function is around 1.0, so that means it is the electrons are highly localized. If it is around 0.5, it is highly localized, delocalized. If it is really less, then there is the charges are really low. So here you have really high electron localization function of the nitrogen atoms. So these are the non-bonded electrons in the nitrogen. So wherever we put the molecule, it always prefers. So this holy site is the potential site to trap the molecules. So this then we have calculated the band structure for hydrogen and halogen molecular absorption. The molecular absorption on C2N monolayer introduced the intermediate bands in the band gap, and that reduces the band gap value. So yeah, so we also calculated the charge transfer mechanism in the system, because when you put the molecule, the molecules tend to draw electrons from the C2N layer due to their high electronegativity, and they also introduce the new bands which significantly alters the photocatalytic properties. So from bandage positions, we come to a conclusion that the iodine substituted C2N system is more promising for water splitting because of the optimum band gap and then the bandage suitable bandage positions. And next, we have constructed the structure with CDS and CDSC layer, because the cadmium sulfide and cadmium sulfide is a promising photocatalyst. They have a really good efficiency. So we want to check the CDX layer and then the CPN layer. If you make a heterostructure, whether it improves the water splitting activity. Yeah, so we have constructed the heterostructure, and then is the charge transfer plot. From here, we can see that almost all the charges are redistributed in the interface region. So we calculated the density of states and then bandage questions. So from density of states, we can see that this heterostructure has a type 2 band alignment, because we can see here. Here the CPN layer, the conduction band minima is from the C2N layer, the valence band maxima is from the CDX layer. Here, the conduction band minima is from C2N, and then the valence band maxima is from CDSC. So this makes a type 2 band alignment. The type 2 band alignment is really promising for water splitting, because the charge carriers will be spatially efficient in this material, so that will reduce the water into hydrogen and oxygen. Here we have we align band edges with 3 different pH, even at pH equal to 0, because seawater, the pH of the seawater is 8, so even this material can be used to split the seawater. So the band edges are straight at the water redox reaction. So, and then you have this type 2 band alignment. So the electrons will electrons at the CDSC will oxidize, and then the electrons at the conduction band will reduce, and the holes in the valence band will oxidize the water into hydrogen and oxygen. Yeah. So in the next work, this is we calculated the reaction mechanism. So B into monolayer. So this is a B into monolayer. It is a kind of graphene-like system with active band gap of 2.23 electron volt. This is the theoretically predicted material. It possesses high mechanical, thermal, and dynamical stability. The reported carrier mobility at room temperature is higher than many other two-dimensional material. So all these exceptional properties are making the B into monolayers promising for water splitting. So to check how the charges are present in the system, we have calculated the charge band decomposed charge density at valence band maximum and the conduction band minimum. So from this, we can see that the charges at the valence band maxima is from the nitrogen PZ states, whereas the conduction band minima is from the hybridization of both beryllium and the nitrogen PZ states. So to evaluate the stability of the system, so we calculated the cohesive energy. And then the calculated cohesive energy is 5.03 electron volt per atom, which is higher than the other well-known two-dimensional material. So this indicates that the bonding in B into layer is strong and stable. Again, to check the dynamic stability and thermal stability, we have performed a phonon calculation and then molecular dynamics. Same, the total energy fluctuation is minimum, and then the structure at the end of the simulation is planar, and there is no big structural distortion. So the material is stable at room temperature. Again, the material is also stable dynamically because of the all the vibration modes are real. Yeah, so photocatalyst. So we are using photocatalyst to split the water. So what photocatalyst will be in an aqueous environment. So it is also essential to check material stability in aqueous environment. So we place the monolayer, the B into monolayer, in a water box with a fixed density and calculated the pair correlation function. So if you see the pair correlation function around this region in the long range or region around 8 to 12, you have a sharp peaks. This indicates that the material remains crystalline. This is due to the fact that the crystalline materials show a long range order feature whereas the amorphous material show long range disorder feature. So you have a short peaks in the long range order, so the material remain crystalline, whereas the pair correlation function for water, there is no the long range order. So this indicates that the material is stable in aqueous environment, and it is little buckled. This is due to the interaction between the water molecule, but the material is stable in aqueous environment. Yeah, so the another important factor is to check the material is stable against the photocorrosion, because you have the material in aqueous environment, and then you pass light, it can corrode, or it can get the photocorrosion. So to evaluate the photocorrosion, we have calculated the pore bags diagram. This is the diagram. So this shows that if the Gibbs free energy of the pore bags value is 0, the material is stable. If it is around between 0.5, the material will decompose into one of its solid phase, and that solid phase will form a passivation layer on the top of the material, and that will further prevent the corrosion. So the pore bags diagram shows that the BN2 monolayer has a thermodynamically stable in the alkaline region, and then little bit from in the acidic region. Whereas if you see at the pH equal to 0, the minimum value of the free pore bags free energy is found to be a 0.24 electron volt. This is reasonable because there are well-known semiconductors. They are experimentally stable, but their pore bags free energy values are as high as 0.5 electron volt. So this is 0.24 electron volt. So the BN2 will be stable against photocorrosion by forming the solid phases on top of the surface. The electronic properties of a BN2 monolayer, it's a direct band gap. Yeah, so we have when maximum conduction minimizes the same point. So it's a direct band gap material, and we calculate the band gap using different functionals, PB, HSEN, GW. Okay. So usually PB will underestimate. Hybrid function will improve the band gap. However, if you want to predict band gap which is closer to experimental value, we need to go for the GW band gap. So we calculate the GW band gap, which is 0.16. So we calculated carrier mobility, or the effective mass. You see the effective mass of electron and holes on both directions, gamma to K and gamma to X is lower than 0.5. So the mobility will be really excellent in this material. And now we want to look at the reaction mechanism involved in hydrogen evolution and oxygen evolution reaction. These are the mechanism for hydrogen evolution reactions. So this asterisk shows that the surface of the material. So the water molecule will come and then absorb on the material surface. It will convert into OH by producing hydrogen. By producing hydrogen electron. Okay, so it's a proton-electron pair. And then the OH will form absorb O by producing again the next hydrogen electron pair, proton-electron pair. Sorry. Then the third step, the second water molecule will invert, and that will form OH on the surface by releasing the third electron, proton-electron pair. The final reaction step, the OOH will produce oxygen gas that will leave from the surface by releasing the fourth proton-electron pair. So these are the 4 steps involved in the oxygen evolution reaction, whereas the hydrogen evolution reaction can proceed via 2 different pathways, either by adsorbed hydrogen or the adsorbed H3O. So we considered both pathways in our study. So this is a geometry optimized geometries of optimized intermediates. We can consider different positions, and then these are the lowest energy positions. So OH adsorbed, O adsorbed, and OOH adsorbed on the surface. And this is a free energy diagram. We calculate the free energy diagram at 0 volts. The electrode potential is at 0 volts, and then the equilibrium potential 1.23 volt and 2.06 volt. If the electrode potential at 0 volt, first reaction step and then the third reaction step is all the reaction steps are uphill, then the except the final reaction step. Whereas these two reaction steps is more energy demanding, and then the formation of OOH is the rate limiting step here. So we calculate again the free energy at the equilibrium potential. Here at the equilibrium potential, two reaction steps are uphill, whereas the other two is downhill. So if you increase the electrode potential to 2.06 volt, all the reaction steps are downhill. So in order to have the hydrogen evolution in the BN2 system, the electrode potential should be around 2.06 volt. Also, if you see the first reaction step of forming OH, and then the third reaction steps of formation of OOH is more energy demanding, and these steps also involves a proton extraction from water. So in order to check the barrier, we have calculated the barrier energy using Nudge elastic band method, like extracting a proton from water, and then the energy barrier is around 2 electron volt, whereas the barrier of the free energy is around 2.06 electron volt. So this energy barrier does not affect the overall over potential of oxygen evolution reaction. Since the free energy profile for hydrogen evolution reaction, we calculated along two different pathways, along adsorbed hydrogen and along adsorbed H3O. So from here we can see that the hydrogen evolution reaction will proceed via H3O pathway because the free energy is lower than that. Then the over potential, this HER is around 0.52. So we calculated the band edge coefficient using the band gap from GW. You can see that the valence band and conduction band coefficients of BN2 Monolayer located at 2.60 volt and then 0.56 volt away from the releasing potential. So this indicates that the photo-generated electron at the valence band can oxidize the water, and then the photo-generated electrons at the conduction band can reduce the water spontaneously without aid of any co-catalyst, because the band edge portion is higher than the over potential of the material. In the next study, we have calculated the reaction mechanism on rhodium integrated graphene SiC. Yeah. So somebody is talking. Okay. So main motivation of this study is producing a large quality graphene is really challenging for various applications. However, the epitaxial growth of graphene on silicon carbide have attracted great attention for high quality graphene. So this is SiC substrate, and then you have epitaxial growth of graphene. And there are earlier reports shown that if you pass hydrogen gas, this hydrogen intercalate between this layer, and that will break the bonds between carbon and silicon and make a freestanding graphene layer. So this intercalation procedure will also work for other atomic species. There are almost all transition metal work for all transition metals. When you put the transition metal, it will intercalate between this layer and form a freestanding graphene. So in this study, we want to check how the rhodium intercalation alters the catalytic properties of graphene. So this is a graphene on SiC surface. You see the graphene is having a strong covalent bond with a silicon, and this is the corresponding band structure. And then if you see the band structure, the direct bonds are overlapped with the valence band of the SiC, and then the conduction band of graphene is also merged with the conduction band of SiC. So this opens a huge band gap in this material. And then when you intercalate the rhodium atoms, the buckling of graphene is little low, but still there is little buckling. This is due to the charge redistribution between the metal atoms and then the graphene. So we have a charge transfer plot. So this indicates that when you intercalate rhodium atoms, this will form a pristine graphene layer. And now our further study will focus on the CO2 reduction on graphene. Yeah, so this is the free energy diagram for CO and formic acid from production. So this formation of CO and HCOH is a two proton electron step. So the first proton electron, will form absorbed CO2 into a COOH or HCOO. So from this free energy plot, we can see that it always prefers to, form COOH rather than HCOO because of, the free energy, because of the Gibbs free energy. Yeah. Then second proton electron step, the COOH will form either CO or HCOOH. So from this free energy diagram, we can see that formation of HCOOH is more favorable than CO formation. So this material, RH intercalated graphene, will form formic acid through a COOH rather than a CO. So we calculated the free energy diagram for CH3OH production, it's methanol production. So first, it's a 6 proton electron step. So the first CO2 will convert into COOH, and this is the red determining step. And then the next proton electron will form formic acid, and then it will either form CHO or COH. But this step is energy demanding, so the free energy is really high. So it will go to CHO, then CH2O, then CH2OH, and then finally it will form a methanol. So the free energy diagram of methane production. So again, the step is similar, same until CH2OH, and then from CH2OH it will form CH3OH. Then it will form a CH3, and then it will go to a methane, and then the methane will absorb from the surface. If you compare these two free energy diagrams, formation of methanol is more favorable than the formation of so the formation of methane is more favorable than the formation of methanol. This material will produce methane when you pass the CO2 gas. And the other reaction is the hydrogen evolution reaction. This is a side reaction, and it's an unwanted reaction because when the material, the first electron hole pair, the CO2 can form COOH, or it can also form hydrogen in the first reaction step. So this is an unwanted side reaction. We don't want this. It has to be suppressed if you want a good CO2 reduction catalyst. So we calculate the Gibbs free energy of producing hydrogen gas. The O potential is 0.43 here, 0.43 electron volt here, whereas here the O potential of forming COOH is 0.36. That means here in this catalyst, the HER side reaction is suppressed because of this limiting potential, and then this material always prefers for CO2 reduction than the hydrogen evolution reaction. I think I'm done. So this is the conclusion of my talk. So we have used several strategies like substitution, and then the absorption of molecules, then electrostructure construction to improve the water splitting activity of C2 and monolayer. Also, we studied, the mechanistic understanding of BN2 monolayer using DFT study. So it reveals that this material can split water without the aid of any co-catalyst. Also, the rhodium intercalated SiC graphene catalyst can electrochemically reduce a CO2 gas into methane or methanol. Then, nowadays the DFT can accurately predict material properties for various applications, and then the rapid development of DFT methods and computing power has made it possible to understand various catalytic processes at the atomic level. Yes. Thanks for this opportunity. If you have any questions, you can ask me.
Yes, thank you, sir, for your nice presentation.
Yeah.
Yeah, it's definitely the high-opening topic for the blooming researchers. Any questions from participants' side? So before, shall I ask some clarifications, sir?
Yeah, sure.
Yeah. So your complete work is on VASP code, sir, or some other code you used, sir?
No, it's on WASP. Yeah.
Yeah, okay. So as a computational material science researcher, I am very proud about your work, sir.
Thank you so much.
Yeah, I am also working in the same VN2K and VASP.
Oh, okay, nice. Yeah. Okay.
Actually, my doubt is, you are not went for any experimental parts, sir? Have you done any?
So I'll show. Okay, so this last work is collaboration with a experimental group. So they synthesized this rhodium intercalated silicon.
Yeah.
Okay. So they want to see whether the rhodium will form a pristine graphene.
Okay.
At the same time, whether will either form methane or methanol. So I just present only the theoretical results. It's a collaboration between experimental people. Yeah.
So you have a proof for CO2 reduction, right, sir?
Yeah.
Yeah.
Now also I want to mention here this previous talk on CP and monolayer. Yeah, this. So
yes,
theoretically we predicted that this material is promising catalyst for water splitting, and there is a company they developed the electrochemical cell based on this material, and then they asked us to evaluate that project before releasing the project to the market. So this theoretical calculation is accurate and predicted.
Sir, you have shown one diagram for the thermal and dynamic stability, sir. Sorry, I could not able to get the slide number.
Okay, I will go.
Yeah, actually, is it directly available or any additional package you have used, sir? Not this one.
Okay. So it's a VASP calculation only, but we have there is a separate code called Phonopi.
Okay.
So
Right.
you have to install with the VASP and then to get this one. And this is it's a ab initio molecular dynamics only, so it is available with VASP.
Okay.
To get that, you need to have a different package installed.
Yeah. Okay, sir. Then actually in some papers I have studied that oxygen evaluation reaction can overcome than a hair rate, that hydrogen evaluation reaction. So is it, as a clarification only, I need to ask this question. So is need to study about ore rate too?
What
oxygen evaluation reaction studies we need to carry over, sir?
I don't get it. What? Over it? I don't get it. What?
Yeah. Yes, sir. Actually, in your studies, you completely mentioned about HER, hydrogen evaluation reaction rate.
Yeah.
Is it necessary to study that oxygen evaluation reaction too? Or
I have done oxygen evaluation also, right?
No. I'm asking you. Is it enough to study about HER?
Okay. No. Okay. So you can see here it's a bifunctional water splitting catalyst. So you in your material you have both oxygen evolution and hydrogen evolution also.
Yeah.
The thing is, some material will be good for only hydrogen evolution reaction.
Yes.
Some material will be good for only oxygen evolution reaction. Yeah. So you need to combine these two to have the overall material. But this one is promising for both reactions. Without any co-catalyst, you can split water.
Okay. So this is what I need to clarify.
Yeah.
Okay, sir. Sir, can you show that silicon carbide band gap?
Okay. This one?
Yeah, yes, sir. It's actually semiconducting material is preferable for this kind of study, sir. I'm asking as a clarification.
Yeah.
Yeah, definitely, because band gap.
Okay, so it is.
Here,
Okay, it's an electrocatalyst actually. So here the semiconductor or metal doesn't matter, but the only thing is you should have only the absorption energy matters. So your material should not absorb too strongly or too weakly. Okay.
Okay.
It should have
Okay.
alkaline.
Okay.
So it doesn't
Okay.
matter.
Even though metals also, if based on
Yeah.
absorption energy, we can select, right?
Yeah,
sir?
yeah. Yes.
Yeah. Okay. But here band gap actually is a semiconducting material, right, sir?
Yeah, it's a semiconductor material, but yeah, you can see a little overlap.
Yeah. This is what actually as a clarification I need to check.
Yeah. So this is just a GHA with not really
Okay.
accurate. So maybe,
The exchange correlation potential you have to check. Yeah. Okay, sir. Thank you.
Yeah. Okay. Thank you.
Yeah, just to check the diagram again because I noticed some of the bands may overlap, so that I just want to see again. Yeah. Okay, sir. Thank you for your nice presentation, sir, and very informative too.
Thank you so much.
Yeah. Any questions from participant side? You can unmute yourself. You can ask, or if you are unable to unmute, please ask in chat box.
I think no questions. Huh?
Yeah, no more questions.
I think no more questions, Ashwin.
Okay.
Yeah, thank you, sir. Thank you for your wonderful informative session because it is an upcoming idea which is very helpful to our environment.
Thank you so much.
Yeah, thank you, sir.
Thank you, Ashwin.
Yeah, okay.
Thank you for accepting our invitation and deliver the task.
Yeah, thank you for inviting me.
Questions from participants, I will send your mail ID.
Yeah, sure. Yeah,
Thank you.
Yeah.
Thank you very much.
Yeah, okay, thank you so much. Bye.